Okay, today we're going to talk about electrostatics and Coulomb's law. But first, let's do a quick review, and you'll see why soon. Let's do a quick review of Newton's law of universal gravitation. So if you recall, that law told us that the force of gravity between any two objects is equal to capital G times m1 times m2 over r squared, where m1 and m2 are just the masses of the two objects. R is simply the radial distance, or the distance between the centers of the two objects. And G is the universal gravitational constant, rather. Okay, so G is equal to 6.67 times 10 to the negative 11th. And you can figure out the units on your own, but I'll give them to you. It's newtons meter squared per kilogram squared. How would you figure that out? It's pretty simple. You would just have to take a look at what we want to end up with. We know it's a force, so we want to end up with newtons. So G better have newtons in there. And then it has to have something to cancel out the kilogram squared. So we have to get rid of this kilogram squared from the two masses. And we have to cancel out the meter squared from the radial distance squared. So that's how we come up with those units. Pretty straightforward. Okay. Now, if you think about this, what this law is saying is that any two objects with mass will exert a gravitational force on each other, okay? So mass is really the key here. Mass is the key to the gravitational force. So now let's go back and let's take a look at something you may have seen in chemistry. You probably talked about a proton having a positive charge and an electron having a negative charge. And if I asked you if these were the only two things in the universe, what do they do to each other? Hopefully you would come up with they attract. And that word attract is a word that people in chemistry like to use. But we don't like that word in physics because it doesn't mean anything to us. We haven't defined it. What does it really mean in physics? Well, it means that if I were to have these two objects and holding them still, and then I was to release them, they would start accelerating towards each other. Well, if they're accelerating towards each other, there must be a net force. So now let's take a look at just the proton. If the proton starts accelerating towards the electron, there must be a net force that points in the direction of the electron. Well, if there's a force, some object has to be exerting that force. So what object is exerting that force on the proton? Well, you guessed it, it's the electron. But it's not a gravitational force. Sure, there is a slight gravitational force, and we're going to calculate that in a little bit. But there's also a bigger force. And let's see if I can prove to you how I know that it's not a gravitational force. Because if it were a gravitational force, and I had two electrons, and I was holding those still and then release them, would they attract? No, obviously not. You know that they're going to repel. Have you ever seen a gravitational force cause repelling? No, it's always an attracting force. Gravity is always an attracting force. So we know that it's not the force of gravity that is attracting the proton to the electron. So then the question becomes, what is it? Well, you know that it's the charge. You know that any positive charge thing is going to attract, in the terms of our chemistry teachers, attract a negative thing. So what we call that the electrostatic force. Some people guess that it's a magnetic force. It's not magnetic either, okay? But it's called the electrostatic force. And it's the force that results from an object having charge. And it's going to look very similar, and we call this Coulomb's law. It's going to look very similar to Newton's universal law of gravitation. And it looks like electrostatic force is equal to some constant, we're going to just call it K, times the charge of each object, and we're going to use Q to stand for charge, lowercase q, divided by the distance between them squared. Okay? Now, you have probably measured, if I asked you, well, what's the charge of an electron? You haven't measured it, you were told it. If I asked you what's the charge of an electron, you probably know that, an electron has a charge of -1. Well, -1 what? Well, that's the thing. We're basically just counting electrons when we say it has a -1 and a proton has a +1 charge. So we call that the elementary charge. That's what you're used to using in chemistry, because that's super helpful when you are combining elements into compounds. So it's very helpful to know that. For instance, I'm sure you know that sodium has a +1, likes to be a +1 charge, and chlorine likes to have a -1 charge, and that's why they like to join up together into salt. Okay, but having this is actually a very, very tiny number. okay, this elementary charge with 1 electron, we're not going to have many situations where we're dealing with 1 or 2 or 3 electrons. So we're going to define charge with a different unit, okay? And we're going to use coulombs for charge. So we are going to say that Q is charge, and we're going to measure that in coulombs, C-O-U-L-O-M-B-S, okay? And our conversion for elementary charge, so 1 elementary charge, is equal to 1.6 times 10 to the negative 19th coulombs. You could also use capital C to stand for coulombs, okay? So we know that 1 electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. Just for future purposes, because you're going to need to know this, okay, the mass of an electron, you were probably told that an electron doesn't have any mass. That's not true either. It has some mass. It's just very tiny, especially compared to a proton or a neutron. So the mass of an electron is 9.11 times 10 to the negative, sorry, let me undo that. I get too used to writing the same exponents, times 10 to the negative 31st kilograms. That's a teeny tiny number. The mass of a proton, just for reference, is 1.67 times 10 to the negative 27th kilograms, and that's about 1,000 times bigger than an electron. All right, so now the only other number we need is this value for K. All right, so if we are going to measure our force in newtons, we know that we're going to measure the distance between our 2 charged objects in meters, and we're going to measure Q in coulombs. We can see that K, I'll just give you the number, is 9 times 10 to the 9th, but the units must be newtons meters squared, similar to our G. But instead of dividing by kilograms squared, we're going to divide by coulombs squared. Okay? So now you have all the information you need to determine, okay, so I'm going to ask you to do this, so go ahead and get your calculator out. Pause the video, get your calculator out. And I'm going to ask you to determine both the gravitational force and the electrostatic force between a proton and an electron that are 1 meter apart. So go ahead and pause the video and do that now. Okay. You should have found that the force of gravity is 1.01 times 10 to the negative 67th newtons, and the electrostatic force was 2.3 times 10 to the negative 28th newtons. Obviously, the electrostatic force is significantly larger than the gravitational force. So what does that mean? That means that if I have a proton here and an electron here, and I want to do a free body diagram, let's say just for the electron, there are 2 forces acting on there. Let's assume for right now that there is nothing else in the universe, just this proton, just this electron. There are 2 forces acting on there. You've already calculated the magnitude of those forces. Now, you might have had a negative sign for the electrostatic force, but just like when we calculate, for instance, the spring force, we ignore that negative sign because we're going to figure out the direction on our own. The negative sign just tells us, it gives us a hint for the direction. But we can figure that out on our own because we're going to do a free body diagram. So let's take a look at this electron. There are 2 forces on there. You calculated them. The electrostatic force is going to be going which way? Let's see. It's an attractive force to the proton, so it's going to look like this. Now we have the gravitational force. The gravitational force is also going to be going to the left, but if I had to draw it to scale, I couldn't even do it. It's so much smaller. So that's why when we have a situation like an electron and an electron, right, like this, we know that the electrostatic force would be going way to the right. The gravitational force would be too small to even put on there because it'd be so much smaller, almost 40 orders of magnitude less. Not 40 times, but 40 orders of magnitude less. That's a lot of zeros behind that decimal point, okay? So now you should be able to go to Schoology, get the Coulomb's law problems, and practice those up. Do remember that the forces are vectors, okay? So if a problem asks you, and I think problem 5 will, if a problem asks you, hey, what's the total force that's acting on this object? Remember, it's a vector, so you're not going to just be able to add those forces by scalars. Make sure you take direction into account and use your knowledge of vectors. Okay, that's it for electrostatics.